Welcome folks to part 1 of our 35th lecture in MAT353. This is our penultimate lecture in this course. And we're going to begin properly in our final topic, which is Green's theorem. So I think what's going to play out is the two parts of this lecture. We're going to cover the two different versions of Green's theorem. And we may run a little bit long, especially given some sample problems today. But in our next and final lecture will be an abbreviated lecture where we'll just sort of tie up some loose ends. We'll consider some connections between some of the big ideas that we've considered, and we will let that be a somewhat shorter lecture here, the final lecture that we will cover next, lecture 36. But for now, let us take up this final major topic, that being Green's theorem. There are two versions of Green's theorem, one that corresponds to the idea of curl and one to the idea of divergence, which we've just recently discussed. And so in part 1, we're going to be thinking about Green's theorem curl form. And Green's theorem applies to a special kind of curve known as a simple closed curve. We have already been talking about closed curves. In particular, we've been thinking about what the fundamental theorem of line integrals says about the line integral of a conservative vector field along a closed curve. If you remember, you always get 0 for such line integrals. But those closed curves were allowed to self-intersect, essentially. They could cross over themselves as long as they eventually ended where they had begun. Simple closed curves are closed curves, but they do not have any self-intersections except for the endpoints. So they are closed curves, they do end where they began, and yet that is the only time that the curve meets itself, effectively. So the bottom two pictures here are of simple closed curves, and the third picture here is of a closed curve, which is not simple because it does have this non-endpoint self-intersection. Alright, so simple closed curves are nice because they divide the plane up into an interior region, which we're going to call D, and then the exterior region outside of the curve. So we will state Green's theorem formally in just a moment, but backing up for a bit here, this middle picture where I've got what looks like a circle taken counterclockwise, it's not hard to think about what's the interior, that's going to be the disk that's inside it, and what's the exterior. Over here my curve is a little bit wonkier, but I've still got this interior region here, and then everything that's outside of the curve. So the fact that simple closed curves do divide the plane up into two regions, one that we could call the interior and one that we might call the exterior, that's actually a non-trivial fact. That's something known as Jordan's curve theorem. And it's a particularly interesting example of something that happens in math, where there can be a very simple, straightforward, intuitively obvious assertion that turns out to be really difficult to prove in a mathematically formal way. So something we all can look at and agree upon. Yeah, a circle, you got the inside and the outside, right? That actually turns out to be somewhat tricky, which I think is neat. We're not going to talk more about Jordan's curve theorem. But do bear in mind that simple closed curves have an interior region, which we are going to call D. So let's state Green's theorem curl form. We'll state it formally. We'll concern ourselves with some notational differences between what I do and what Stuart sometimes does. We will spend a fair amount of time thinking about the intuition that underlies this theorem, what it says to us and why we care about it. And then we are going to do some examples and sample problems. Alright, so the statement, it is a theorem, it is an if-then statement. If you have a piecewise smooth curve, which is simple and closed and oriented in a counterclockwise direction. So this is the first requirement, and you'll note that we're not requiring the curve C to be smooth, but just piecewise smooth. So basically, if you can take your curve and you can break it up into a finite number of pieces, where each of those pieces is itself smooth. Another way to say this is that corners are allowed in C, but only a finite number of corners are allowed in C. If there's only a finite number of corners, you can divide up the curve at those corners, and the space between corners should be smooth. So we'll see an example of one in one of our examples or sample problems, I don't recall which, but we'll see an example one of a piecewise smooth curve that is not itself smooth shortly in part 1 of today's lecture. So if you have this curve, simple closed curve, piecewise smooth, oriented counterclockwise, and if we let D be the region interior to that curve, and finally if we have a vector field which is itself C1, so some level of smoothness in some sense applied to the vector field as well, technically C1 means that both P and Q here, my component functions, have continuous first partials. So when I have these three conditions satisfied, Green's theorem gives us the equality of these two vectors. So on the left, I have the line integral of the vector field f, and on the right, I have the integral over the interior of C of the curl of f. So I've got the integral of f along C, and I've got the curl of f taken through the interior of C. And those are the two different types of integrals that Green's theorem is telling me are equal here. Alright, so let's unpack some notation that your book likes to use, and then we will think more about the intuition behind this theorem. So a quick little point on notation here. Your book likes to write Green's theorem this way. So the very top line here is equivalent to what I have said, but with slightly different notation. So on the left-hand side, this p dx and q dy expression that we see here is just my f hat dot dr hat. The book likes this. I'm not 100% why. I like this because I feel like this gives us a better sense of what these line integrals of vector fields mean. We talked about that a bit when we first discussed line integrals of vector fields. That we're looking at the degree to which the vector field lines up with the tangent vector here. My dr hat is effectively r prime in some sense. And so we're thinking about how well does the vector field line up with the tangent vector along the curve, and we're measuring that along the whole length of the curve, that degree of correspondence of the vector field and the tangent vector, getting some sense of what would be the tendency of the vector field to push a bead along this string in the indicated positive direction. So those are the reasons I like this notation. Your book also uses this notation. Basically, the dr is taken to be dx dy, and f is already p and q. So they're kind of dotting it out here. So you end up with the first component of f and the first component of dr hat, and then the first component of f, second component of f, and the second component of dr hat. That's the idea. But this is a translation guide between Stuart's left half and my left half of the statement. Here we have the translation guide between Stuart's right half and my right half. These are closer. All that Stuart is doing here is unpacking the definition of nabla cross f hat. And this is exactly what we defined the curl of f hat to be. So it's simply replacing this expression with the definition of this expression. And this is actually, come to think of it now, likely why Stuart does this, because Stuart doesn't use the cross product notation for two-dimensional curl for good reason, because it's not really a cross product. And I'm using it because I wanted to highlight the connection between the two types of, between divergence and curl rather. This isn't divergence up here, but I did want to highlight the difference and the similarities between divergence and curl. So I'm using that notation where Stuart does not. Stuart uses this notation and then pairs it with this notation for his statement of Green's theorem. So that's that. I'm not going to assign more web assignment problems. We have our final assignment out now. Homework 12 will be your last homework. But if students did want to look through Stuart and pull some problems out of 16.4, the chapter in Stuart that contains Green's theorem, then I definitely wanted to provide you at least with this translation guide between Stuart's notation and my notation so that you can explore some of the sample problems and some of the end of chapter problems given in Stuart. Alright, with that having been said, we will move on to thinking about the intuition behind Green's theorem. What does Green's theorem say? How does a human actually think about and interpret what Green's theorem says? So we're going to take both of the integrals that are involved in Green's theorem separately and spend some time thinking about what they mean, and then we're going to think about what it means for those two things to be equal to each other. So how do we interpret each of the integrals in its own right, and then what do we think, or how do we think about the fact that those two things are equal? What does that mean? So starting with the first integral, we're looking at f hat dot dr hat along C. This is the type of integral that we defined when we first talked about line integrals. We talked about line integrals of scalar valued functions, line integrals of vector fields. This is just a line integral of a vector field. The only difference here is that we've taken C to be a simple closed curve instead of some arbitrary smooth curve. And it only has to be piecewise smooth, in fact. But the difference here is that C is closed, largely, simple and closed. And so if you have your integral, your curve rather, C, which I've drawn in blue, and it's got the positive counterclockwise orientation, and then I've drawn a vector field here in red, what we're looking at is the vector field's dot product with the tangent vector at each point along the curve C. And as we said before, this line integral of the vector field along C it's giving you some measure of the tendency of the vector field to push a bead along C. So if we take C, curve C to be a string, we place a bead on that string, what is the tendency for this vector field to push that bead along that string in the indicated direction? Here it's around that string because the string is actually closed. It's a loop of string instead of a piece of string. And so what is the tendency for f hat to push a bead around this closed curve C? Which is to say, what is the tendency of f hat to circulate around C? So that's what we're looking at here for this line integral of a vector field along a simple closed curve. It gives you sort of how well does the orientation of f hat match up with the orientation of travel along C. In this picture, we would see a positive value for this line integral. If I reverse the orientation of my vector field, we would get a negative integral. And if the vector field simply had no tendency to push the bead along the string, maybe the vector field points straight out across the curve at every point, not along it or in the positive nor in the negative direction, but perpendicular to it, then we would see this line integral being 0. Here in this picture it is positive because the vector field does indeed have a tendency to circulate around C in the orientation given by C. So that's how you interpret that vector, that rather integral. It's much like our line integrals for vector fields, but with a closed curve C. What about this double integral that's involved? So what we're doing here is the curl, as we talked about before, is the tendency of the vector field to rotate locally. So here I'm going interior to my curve C. I made my curve a circle now because those are easier and I got sick of the weird one. So taking a simple curve here, a simple closed curve C drawn in a fairly basic manner, and then D is the interior to that curve C. So I'm taking points interior to the curve, and if I drop a small paddle into this fluid, are there little eddies, are there little swirls that tend to spin the paddle right there in place at that one particular point. And so I'm taking the curl, which I've drawn in red here, is that local rotational tendency. And I'm taking that tendency to rotate locally throughout all of the region. I'm basically summing it up. I'm taking a double integral, which is saying go throughout this whole region, take the rotational tendency local to each point, and add up all of those values throughout the region. So the curl is the local rotation. The double integral of the curl is going to be the cumulative effect of all of the little local rotations throughout the region D, interior to the curve C. And so we had sort of large-scale circulation around the curve, and now we've got the cumulative effects of all the little local rotations interior to the curve. And Green's theorem is telling us that those two quantities are equal. It's telling us that the circulation, sort of the global, large-scale circulation around the curve, around the boundary, is given by the cumulative effect of all the interior locally rotational tendencies, local rotational tendencies. So global circulation around the curve is equal to the sum of all of the local rotations interior to the curve. And that's what Green's theorem says. So we're going to talk more about the practical applications, what kinds of problems could we see that involve this theorem, but this is the big picture stuff that I like to talk about, I like for us to be thinking about, that on the one hand you have circulation around C, on the other hand you have the double integral of curl throughout the interior of C, and by setting those two equal, we're saying that the total effects of curl interior to C are the same exact value as the global circulation around C. So I'm actually going to jump out here. We're going to think about this. We're going to use what's known as Saturday morning breakfast cereal here. This is a great webcomic that involves lots of math and science concepts, but this is a good one. The more complicated the math is, the dumber you sound explaining it. He's talking about something called Stokes' theorem. Stokes' theorem is the three-dimensional version of Green's theorem curl form. So what he's saying here is a theorem that's covered in Stewart, but we're not quite going to cover it in this course. But this is Stokes' theorem. Yeah, that's how if you draw a loop around something, you can tell how much swirly is in it. And that is exactly what we are doing here. We have drawn a loop around a region, and that's allowing us to tell how much swirly is inside of that region. Again, we're doing it for flat regions, and you can do it with more general regions via Stokes' theorem. But yeah, Saturday Morning Breakfast Cereal is a great webcomic. It is off-color and adult-themed oftentimes, so buyer beware in that regard. There is going to be some racy language and some adult situations, but it's funny. So if you're not offended by comedians who work blue, then there's a lot of good math and science jokes coming out of that forum. All right, so this is the intuition behind Green's theorem. Let's think a bit more about practical matters. So Green's theorem curl form provides a link for us between two of the different types of integrals that we've studied in this class. The first being line integrals of vector fields. These are a type of integrals that we've only considered now in the last few weeks of this class. The second being double integrals of scalar valued functions across regions of the plane. This is something we studied in great detail. We thought about polar coordinates, we thought about rectangular coordinates, we've thought about type 1 and type 2 regions. We've got lots of different ways to take double integrals across regions of the plane, such as D. So there is a notational point here. I'm calling this curl scalar valued, and it is, and it's a little bit unfortunate that I'm using the cross product notation there, because cross products are vector products. They typically return vectors. The issue is that this isn't a real cross product. As we discussed when we first discussed curl, it's more properly defined in 3 dimensions, and there it is, a vector-valued cross product, a vector-valued vector product. Here we're just taking one of the component functions is what's effectively happening of that cross product. And so to call it scalar valued and use cross product notation to refer to it, that is anathema. That is difficult for me to do. But I did want to use the cross product notation because we use dot product notation for divergence, and because these notations are largely universal. The sticking point here is that most people don't define curl in 2 dimensions. And I have done so, and I'm using the notation that is most appropriate, most especially appropriate for, or it is especially only appropriate for the 3-dimensional case. It really shouldn't be used for the 2-dimensional case, but forgive me these sins. So a double integral of a scalar valued function versus a line integral of a vector valued function. These are 2 different types of integrals that we've studied, and Green's theorem is setting them equal to each other for specific vector fields in specific contexts. So sometimes this will turn hard problems into easy problems. I could hand you one of these, either one, the left or the right. It could be difficult in the form in which I've handed it to you, but it could be much easier if you convert to the other form. If you use Green's theorem to say, okay, he wants me to find this, but that's hard. Green's theorem tells me that it's equal to this, and maybe this is easier. And so we'll explore that at some examples and sample problems presently. So here is a vector field. It's a little bit weird looking. There's this e to the sine x nonsense, and then there's this 1/2 power on a 4th power polynomial. So that's not great. We're going to let C be the circle of radius 3, taking counterclockwise, centered at the origin. That's easy enough. That I can deal with. And we want the line integral of f along C. So f hat dot dr hat taken along C. Find that line integral of that vector field. And now as we embark on the solution, I note again that f hat looks a bit bad. It's not great. And if you do try to approach this problem in any of the methods that we've seen so far, you will find it to be a difficult road. So you could either first hope that f hat is a conservative vector field, because if it is conservative, its line integral along this closed curve C will be 0. But it's not conservative. You can check that quickly and see that it's not. Then you might fall back to, okay, well I have to use my definition of the line integral of vector fields. I'm going to have to take f hat of r hat, and I'm going to have to integrate that using the definition of the line integrals of vector fields along curves. That also is going to be an issue, so you should not be able to proceed very far if you do that. And finally, you now come to what is your new 3rd option, which is to try to use Green's theorem. So thinking about this f hat, if I were to use Green's theorem curl form, instead of dealing with f hat, I would start dealing with the curl of f hat instead. So let's think about what that would look like. Here's my first component function. I'll call it little p in keeping with the notation in Green's theorem. So if I call this little p, I notice that little p depends on y in a simple way. The complicated part of little p depends only on x. And likewise, if I take little q here, my second component function of the vector field, it depends on x in a simple way, and the complicated version, or rather the complicated summand for little q, depends only on y. This makes it particularly attractive to use Green's theorem, because Green's theorem is going to tell me to take the curl of f hat, and I'll be taking the partial of little q with respect to x, and this will be 0 when I take its partial with respect to x, and I'll be taking the partial of little p with respect to y, making this e to the sine x term 0. So I would rather be dealing with the curl, which looks like this, the partial of q with respect to x minus the partial of p with respect to y, than with f hat. The fact that I realize that I would rather be dealing with the curl of f hat than f hat makes me think, well, why don't I use Green's theorem? So at this point, Green's theorem has begun to present itself to me as an option. I feel like that might make things better. Instead of finding this, I could be looking for this integral instead. But that means instead of dealing with c, I have to deal with d as well. I can see that my integrand is going to get simpler, but am I okay dealing with the interior of this curve instead of the curve itself? So if c is the circle of radius 3 centered at the origin taken counterclockwise, then d is just the disk of radius 3 centered at the origin. And that is easily represented in polar. It's in fact maybe the easiest region to represent in polar. Excuse me, folks. So, both my integrand becomes simpler, and my region is, if I go from the line integral of the vector field to the double integral of curl, my integrand is going to become simpler, and also the region that I'll be integrating over is quite simple. It's simple in both contexts, actually. The circle of radius 3 counterclockwise is not hard to parameterize, but the interior to that is not hard to represent in polar either. So we are going to pull the trigger on this, and we're going to go ahead and attempt the problem using Green's theorem curl form. So my new integrand, what does that look like? I'm taking the curl of f hat. If you take the partial of little q with respect to x, you just get 7. The partial of p with respect to y, you just get 3. And my curl is just 4. So I've gone from dealing with this vector field as part of my integrand to dealing with the constant number 4 as my integrand. And that is a win. Things are simpler here, so that is to the good. Oops. Now let's have a look at the region D. D is the disk of radius 3 centered at the origin. In polar, that's r from 0 to 3 and theta from 0 to 2 pi. So Green's theorem tells me that this line integral of f hat is just going to be the double integral of curl over the interior of c. That's where I'm using Green's theorem to set these two equal. And now this is going to be given by this expression. So d is given in polar, 0 going to 2 pi, and r going from 0 to 3. My dA expression becomes r dr d theta, because I'm translating to polar here. And my curl was just the number 4, as we found. So I can simplify things, I can take the integral, and I end up with 36 pi. And that's a final answer. So, did not have a method to compute a line integral of this vector field in a straightforward way, but we're able to convert that to a double integral of the curl throughout the interior of the curve, and that created a relatively simple problem for us here. And as you know, I love these problems. I love to be able to hand you difficult problems that you cannot approach head on. You have to bear in mind the theory and be able to step sideways and solve an equivalent but much simpler problem instead. Let's give you a sample. So here is another vector field. We've got e to the x cubed, and that's a minus 1/3 y cubed here, and then cosine of e to the y plus 1/3 x cubed. And c here is the curve shown. So I've got an outer circle, x squared plus y squared equals 4. I've got an inner circle where I set that sum of squares equal to 1. And then I'm taking the top half, it looks like, of the space between those circles. And I want to take c to be the boundary of that space. So this fat rainbow shape, c is traversing around the rainbow. So we're going counterclockwise here for the upper portion of it, and then rotating back around and coming back around this way. So it really is counterclockwise rotation everywhere, though it's clockwise across the top half of the little circle, because that's the bottom edge of my region actually. So this is a piecewise smooth curve. It does have corners, but I could cut it up into 4 pieces: the top part of the rainbow, the left straight leg, the bottom part of the rainbow, and the right straight leg. and each of those 4 pieces is a smooth curve. So this is a piecewise smooth, closed, and simple curve. So here's a vector field, here's the curve C. I want you to find for me the integral of f hat along C. Go ahead and pause the video and give that some thought. Alright, let's have a look at it. So again, I would rather be dealing with the curl. Nope, wrong way, sorry. Here's the solution to this problem. F hat is bad. The curl of f hat is going to be better. C is also bad. It's got 4 different pieces. It is possible to break up line integrals along piecewise curves into the separate pieces, though we have not discussed that. C just looks bad to us. It would be hard to parameterize. And its interior D is going to be better in polar coordinates. It's actually another rectangular triangle in polar. So that's going to be relatively simple. So we would rather be dealing with the curl of f, and we would rather be dealing with the interior of C than C itself. And these are the 2 criteria that have to be satisfied for Green's theorem to be reasonable. So we are going to say that the line integral of f along C is equal to the double integral of the curl throughout D. This equality is where Green's theorem is being used. And the curl is going to be the partial with respect to x of the second component function minus the partial with respect to y of the first component function. It is, again, exactly the same deal as in the example, where the complicated parts of these component functions only depend on one variable, and they do so in such a way that when you take the curl, those complicated dependencies are going to drop off. So taking the partial of this with respect to x, I just get x squared. Taking the partial of this term with respect to y, I'm going to end up with minus negative y squared, giving me plus y squared. And of course, as I convert to polar, that is just an r squared term. My region D is got theta going from 0 to pi to get the top half, and then r going from 1 to 2 to be moving from that lower inner circle to the outer circle. And then my dA expression, of course, is r dr d theta. So I pick up an extra factor of r. I can factor this out into the product of 2 simple integrals, and I'm going to get pi over 4 times 15 here for 15 pi over 4 as a final answer. Alright, thank you folks. I do welcome you to look through the examples in Stewart and some of the problems in the back of Stewart if you'd like to look at some more problems. But were you to get any problems about Green's theorem, curl form, on your final, they would be very much like these 2 problems that we've covered today. It is always the case, well, it is often the case in math classes that you get to some of the more complicated material right at the end of the course, and so you tend to get simpler questions dealing with that complicated material. I would encourage you to feel comfortable with this example and sample problem that we've done. Feel free to look for others in the book, but if you are comfortable with these problems and understand my reasoning and what motivated me to try to use Green's theorem here, then you would be in good shape for any questions that could come up. Alright, I thank you folks. I will see you again in part 2 of the lecture today.